a pleasure to be here today to speak to this group. My first interaction with the systems engineering community was the local chapter in DC while I was at the White House, and I really didn't know what I was getting into at that point. My experience there was very good. I really appreciated understanding more about what you guys do and the importance of what you do. So I jumped on the opportunity to come to the bigger event here, and obviously a chance to come down to Australia, which I love to do. A special thanks to Alan and Jackie and Karen for doing what was necessary to get me here. I certainly appreciated it. I do have one confession that I want to make up front, and that is before I left, my wife was interested in coming. Now, she has her own business, and she wasn't sure that she could get away, and I told her, just to console her when she realized that she couldn't come, I said, look, Kelly, they're a bunch of system engineers. How much fun could they be anyway? So now I live in fear that she sees the pictures from last night's banquet of kilts and all sorts of shenanigans. Yeah, I'll have a lot of explaining to do. So, just jump into this issue of space weather. It's been getting a lot of attention of late, and I was reading something, a paper back some months ago about system engineering. It was a NASA published paper, and they talked about a system engineer being like the conductor of the orchestra. And I was thinking to myself, that's a big responsibility, managing that whole orchestra. And now I'm going to come up at the end of this conference and introduce a new piece in the orchestra for many of you, and it's this issue of space weather. So what I'm going to attempt to do over the next 45 minutes is to introduce. Some of you have some background and understanding of space weather. I appreciate that. Others not so much. What I want to do is kind of get everyone on the level playing field and give you all a sense of why space weather should be of interest to you, or should it? That's what I hope to accomplish over the course of the next 45 minutes or so. And how I'll do it is, there's been an awful lot of effort and activity in the policy realm on space weather over the past couple of years, and not just in the United States, but indeed internationally. So I thought the best way to orchestrate and organize this presentation for you all is to talk a little bit, first of all, the reasons behind the policy actions across the top leadership in government circles around the world. So to do so, I'm going to talk about the societal and economic impacts of space weather. If there was one single reason why space weather has emerged as such a significant issue of late, it is that fact, is the impact on the critical infrastructure. I'm going to jump then into some of the space weather types. I want to give you a sense of what this is. If you were to walk into the Space Weather Forecast Center in Boulder, Colorado, what do you see? And what does that look like? So I want to bring you in and get a sense of the operations, what those forecasters, those space weather forecasters are looking at, the alerts and warnings, how it all gets sent out, who cares? So, and each time I introduce a different type of space weather, I will give you the applications piece. This is not going to be a science talk. I'll show you the type of space weather and a little bit about the types of impacts we typically see with it. And extreme space weather events was another big issue that motivated action on this front, on space weather across government circles. It's our keen awareness of various developments and research over the last several years with regards to extreme space weather. And then I'll finish the presentation with some of the response procedures, some of the things that are happening, not just from the policy perspective, but within that policy, some of the actual actions and activities that are underway to build resilience across the globe to this threat of space weather. So let's just jump right into it and talk a little bit about the case for the action. This is just simply a hodgepodge of critical technology that you all recognize, and it, more than anything else, is the motivation behind action at the White House and elsewhere. It's the vulnerability of this critical technology for everything we do today. This audience doesn't need to be reminded how important each piece here is and how they are so interconnected. Any interruption of any of these critical infrastructure can have significant impact on nations. Now, we know that when we get a big storm in the United States and it shuts down the Washington airports or the New York airports and the rippling effects from that. What would it be like if we were without GPS for a day or a week? What would the consequence be? GPS pervades societies today. There are so many different applications. Should we lose GPS for any length of time, the consequence, of course, is going to be very significant. On the upper left-hand side, you'll see the electric power grid, perhaps the biggest motivation for action. Certainly in the United States is the vulnerability of the electric power grid. Folks looked at some of the past space weather events and recognized how big might look. Some of the engineering groups looked at it and said, if we had an event of such magnitude today, what would the consequence be on the power grid? And the findings from some of these engineering groups was very significant. Some had suggested that the vulnerability, again, in the United States is that we could be without power from the New England states through the mid-Atlantic across to the Great Lakes region. Boston, New York, Washington, down through the Carolinas, across to Chicago. Some have suggested the power outage, not only widespread, but long-term. Not measured in hours or days, but perhaps weeks or months. That kind of stuff is going to get the attention of the White House, is going to get the attention of our decision makers, and it did. One thing we had to keep in mind each step of the way, because I will be talking quite a bit about the extreme space weather event. It was really what motivated action within the White House more than anything else. But space weather occurs all the time. Sometimes we get up in front of audiences, we're talking about space weather, and it comes across a little bit as a science-y, fiction-y thing, and say, I don't know what this stuff is, and I don't think I need to care about it. And I like to remind people that it does, in fact, occur all the time. It doesn't necessarily make the headlines. And here's a particular outbreak that occurred in March 2012, not a very, very big space weather event, but just some of the headlines there. You'll see the solar flare knocks out the Light Square satellite. That was the Skyterra 1 satellite, one of the biggest communication satellites at geosynchronous orbit in 2012. It went into a safe mode. They had all sorts of problems. It took 3 weeks to recover the satellite after that shut down. Deep space missions like the one in the Venus mission is mentioned there. And of course, in our DoD circles, space weather is always a significant concern, and a lot of it on the classified side, but you'll still see the headlines as you do there from an Air Force general talking about how the space weather storm interfered with the Air Force satellites. And there on the bottom is kind of an interesting one that occurred in the March 2012 moderate storm outbreak. That INCOSE that you see there, the Federal Aviation Administration in the United States has 3 alerting mechanisms, or 3 alerting levels, I should say, when an aircraft is in distress. The first one is this INCOSE alerting phase. And essentially what it is an aircraft is required to communicate with the ground within 30 minutes at all stages of flight, every 30 minutes. If it has not communicated within 30 minutes, we go into alert phase number 1. And in 2012, this particular flight going from Air Canada was from Vancouver to Tokyo. There was no communication with the aircraft. Now, obviously, ground controllers, the airlines, they want to know what's wrong with this aircraft. Why can't we not communicate with them? So obviously, it's critical they know, is it the equipment? Is it the radio equipment? Is there an aircraft in distress? Or is it space weather, as was the case in this particular situation? In November 2015, just another one I wanted to highlight, it was particularly interesting because I often use this as an example of what motivated action in the White House to address space weather. Just one of the many reasons behind the motivation for this strategy. November 2015. All of a sudden, we get notice, and word comes into the Department of Homeland Security Operations Centers, works its way into the West Wing of the White House, and I'm consulted and say, Bill, what happened in Sweden? I said, I don't know what did happen in Sweden. So the airspace has just been shut down due to a solar flare. We looked into it a little bit. We saw the event that caused the shutdown, and again, it wasn't that big. That headline that you see on the Weather Channel, massive solar storm halts air traffic in Sweden, is in itself a problem because often the media will blow this stuff out of proportion. It was not massive. It was a moderate level storm that shut the airspace down. But the question had to be asked, right? Could that happen in Washington, in New York? Could it happen in Sydney? Why did it happen in Sweden and shut down that Swedish airspace? The answer to the question is we don't know. We need to understand the vulnerability of this critical infrastructure, and this just served as a reminder that we need to do it. It served as a reminder that these impacts do occur, and it also reminds us how little we know about our vulnerability to space weather. Another big piece, and this is a busy chart, and it's supposed to be a busy chart, it highlights another concern. Unlike most anything else, if we talk to the disaster preparedness folks in the United States, a hurricane, a Category 5 hurricane bearing down on a big city like New Orleans and Miami is a great significant concern. But it is local and regional. By impact, yes, of course, there's a rippling effect from it. But if you knock out the power, as I mentioned earlier, in half the country in the United States for a long period of time, and then you realize that the rest of the globe is feeling the effects of a space weather event because, in fact, when these big eruptions occur in the sun, Earth is just a little tiny spot out in deep space. The entire Earth's going to be affected one way or another, and in a very extreme event, we think the consequence will be very significant across the globe. October 2003 was just a little sampler. It wasn't a huge event, but it was an interesting outbreak that went on for the best part of 2 weeks. I'll show you the actual activity that occurred with that here in a minute. But you'll see it was all sorts of impacts. The power grid was shut down in Malmö, Sweden. Japanese lost a $600 million satellite. Aviation, airlines were rerouting flights left, right, and center because of the radiation levels and impacts on communications. GPS systems, we got reports from around the world of GPS being inaccurate or in some cases just not available whatsoever. So again, just recognize this space weather is global in nature. So let me talk a little bit about some of the space weather types and just give you a sense, again, if you're in the forecast center, what you would be looking at and why you should care about it. So first, what is space weather? We talked about the impacts already. What is space weather exactly? It's emissions from the sun, eruptions largely from the sun. It emits different types of radiation, other types of emission that affects technology here on Earth. It is as simple as that. It's essentially three different types of emissions. The electromagnetic spectrum, across the spectrum. Should we get a very, very big eruption, we'll see the X-rays, gamma rays, radio waves, light waves, we see across the spectrum on the very, very big events. Speed of light, that 93 million miles from sun to Earth. Only takes 8 minutes to get here. As soon as we're seeing it, we're feeling it. The second piece of a major eruption is the energetic charged particles that flow in to the near-Earth orbit. Happens sometimes as quick as a third the speed of light. So this is the energetic protons, not the photons. These are flowing in and will respect Earth's magnetic fields and concentrate often in the higher latitudes. Sometimes very high energy particles that affects lots of different systems, especially in space. And the last piece of the emission that's very, very significant, the magnetic field. When these eruptions occur in the sun, and I'll show you an example, the sun essentially shoots a magnet out into space. Sometimes that magnet's coming right towards Earth. Earth has a magnet too, right? Our own magnetic field. And when these two magnets come together, we get a reaction. And how intense the reaction is, that's our geomagnetic storm, will dictate the impact largely on the electric power grid. Let's talk about the three types here and give you some examples. Big black box up here. I'm just going to put it into motion here, and you'll see what a flare looks like from the limb of the sun. You see that bright area? The forecasters in the forecast center are looking at that bright area. It's rotating into view, and all of a sudden that happens. That brightness, that brilliant flash bulb that just went off, that's that violent explosion. That's the solar flare, typically associated with a big sunspot cluster. energy equivalent of 100 million hydrogen bombs. So we're seeing that, so we're going to see the emissions across the electromagnetic spectrum, and it is going to affect technology here on Earth. It'll impact GPS systems, it'll impact communication and ground-based systems, and it will impact radar systems. When one of these big eruptions occur, we have to get on the phone with our DoD counterparts and get that information into them immediately. Why? These emissions are jamming our national defense systems. Now, what's causing the jamming? We need to know very, very quickly what might be happening there, and obviously space weather, that situational awareness is critical on determining the next steps once you find out what's affecting your national defense systems. The image you see there of Earth is it's a nice example I wanted to show you of one particular type of impact, and that is the impact on HF communications. If you're flying over a remote area, particularly the Atlantic, Pacific, the large oceans, if there's no one down below you, typically if there's someone down below you, the airlines will communicate via line of sight on VHF. If they're out over the Arctic, on the polar routes, Atlantic, Pacific, they use HF communications still, 3 to 30 megahertz. Why? Well, it's effective. You just bounce it off the ionosphere, and you can make good communication from mid-Atlantic into the air traffic control centers in Ireland and Long Island. It works great, and very importantly to the airlines, it's cheap, it's free, whereas the satellite communications is not. So if you look at the Federal Aviation Regulations right now, you'll realize that the HF communications is the primary means of communication over the remote areas. They do have backup, obviously, but HF communication is still the primary. You look at that map, and I'm going to put it into motion to show you what happens, the ionosphere, when one of these big flares occur. You see the little color bar underneath the map from magenta there up to the red? When you see red on this map, that is total loss of HF communication capability. Now, this is a daylight side effect. The flare occurs on the sun. As mentioned, across the magnetic spectrum, we're getting this blast of radiation, including the X-ray and extreme ultraviolet radiation, which is impacting the ionosphere further, ionizing the ionosphere and changing the characteristics of the ionosphere, where an HF signal will no longer bounce. It'll be absorbed. And within a minute of the eruption occurring, that HF capability is lost. That particular flare that I just showed you on the limb of the sun, it erupts within seconds. Watch what happens with the map. For 2 hours and 53 minutes was the total recovery time. We lost all HF comm capability in the Caribbean, a large chunk of the Eastern Pacific and Western Atlantic due to this event. Airlines know immediately it's a solar flare, because you see the image on the lower left-hand side? That's the air traffic control center, one of them in New York, and that image that you're seeing running right now runs 24/7. So they know, again, situational awareness is critical. What's causing the problem on their ability to communicate with an aircraft? How does it affect GPS, these solar flares? GPS works on 2 key frequencies, right? 1.2 and 1.6 gigahertz are the 2 frequencies. Well, the sun emits at 1.2 and 1.6 gigahertz all the time. It's background noise. We know it occurs. We engineer around it. We build our spacecraft, our GPS satellites, our receivers, with the understanding that that noise is always there from the sun at those frequencies. But something quirky happens, obviously, during these big flares. The enhancement on those frequencies can be very, very significant. And on this event in December 2006 is the best example we have, because it was magnificent. We didn't even think it could happen, that we'd get an eruption this big. We measured a 1.6 gigahertz frequency background in solar flux units, and it's typically about 100 to 120 solar flux units. This flare occurred, you see it on the green image there, that very brilliant bright area. And the emission at 1.6 gigahertz was tremendous. The background level went from 110 solar flux units to 1 million. Now picture the change in your signal-to-noise ratio now, and you're trying to capture that signal, it wasn't happening. I'll put it into motion and you'll see the IGS is the International GNSS system with receivers around the world. Green is good. Green is worth receiving the signal. It's like that most of the time. It's part of the problem. It's there 99.999% of the time. But just in certain incidents, it is not available. And this was one. And here's what we have to think about. What is the consequence of losing GPS? In this situation, not for hours or days, just 10 minutes. But if all of a sudden you do not have GPS, what is the consequence on what systems? Just for that short amount of time, because as many of you know, it's quite significant. If you're driving on the highway and you're using your Garmin, your TomTom, and the GPS is not working, whoop-de-doo, you'll figure it out. But if you're landing a plane in low IFR, low visibility, low ceiling, strong crosswinds, and you're relying on GPS, or if you're on a DOD or any defense activity, national defense activity, and you're relying on GPS and all of a sudden it's not available, the consequence can be very significant. And this is just an example. I'll put it into motion, and this is at the 1.6 gigahertz, and you'll see even with the smaller bumps at that frequency, you'll get some levels of interference, but then when the big one occurs, you'll see loss of lock, complete northern, southern hemisphere, practically all stations for that short amount of time. It's interesting, I show you this, but I always like to give you the ground truth from others, the end receivers, not Bill Murtagh, the space weather guy, but this came in from the GIPSOC, which is the GPS Operations Center in Schriever Air Force Base in Colorado, and I quote, there was widespread loss of GPS in the mountain states. 1 minute the aircraft everyone's working hunky-dory, or they're getting 7 to 9 satellites, and all of a sudden 0 to 1. So it's again just short-lived, but it can be very significant impact. So the second piece of the emissions, the energetic particles, we call them the solar radiation storms. We see a big flare like the one you see on the green image there. Our sensors for the energetic particles, for the protons, sit on board the geosynchronous satellites. We measure million electron volts, 10, 50, 100 MeV protons. They're the energy levels of significance to us. And of course, they are protons. They will respect magnetic field, so the concentration will largely be in the polar regions. When they occur, these big energetic particle events, they impact a lot of different technologies. Every satellite company in the world, bar none, gets the information from us on the particle environment at geosynchronous orbit. It causes all sorts of havoc to satellites. Most of the time, not significant. You don't hear about satellites collapsing, falling out of the sky or anything like that, but it does cause a lot of headaches, and these folks need to know what course of action, when they pull out that book, what is step A, B, C, and D? It depends on what's causing it. If it's solar flare, particle event, etc., it gives them, obviously, the information they need to take that the correct course of action. Aviation has become an interesting the aviation community, an interesting customer for this particular product, the radiation storms. This is particularly, well, it certainly applies to Australia, not as much Europe, but for the Americas and for Asia. If you're flying in particular from North America to Asia, what's the common route these days? Right over the pole. Last year was 16,000 flights flew polar. As soon as we get one of these radiation storms and we reach that 1,000 particle flux unit at the 10 MeV proton level, they're out of there. That information goes to United, Delta, it goes to Qantas, it goes to all the major airlines that fly high latitudes. Once you get inside the 82-degree circle, this is particularly important for the US, Canadian, and Asian airlines. When you get inside the 82-degree circle, you're no longer communicating with a GPS satellite. The curvature of the Earth just prevents that. So you're back to HF communication or some LEO, iridium, depending if you got the right equipment for it. As soon as you're inside that 82-degree circle, one of these big energetic particle events occur. You'll see in the upper right-hand side, the red area. Your HF capability is gone. And federal aviation regulations require you maintain the communication. If you know the communications will be unavailable, you don't go there. As simple as that. So as soon as the information gets up into Chicago and United Airlines and Dallas down to American Airlines and Delta in Atlanta, they start rerouting flights away from the poles. I was talking to the United guys. I said, Mike, what do you tell the passengers when you're rerouting a flight due to high levels of radiation? He says, Bill, you can be darn sure I don't say radiation. They say typically weather. Space weather. What does it look like, one of these radiation storms? One of the curses in our business, in regular weather, people know what a tornado is, and a hurricane, and a blizzard. Why? Because you can feel it and you can see it. In our business, it's difficult sometimes, especially in radiation storms. You got flights rerouting over the polar regions. Why do people say, we're not feeling anything? You can't see it, you can't feel it. Here's one way we see it. It's quite interesting. That blue image you see there is called a coronagraph. It's an instrument that sits on board one of our satellites in space. And what you're looking at there is we're creating an eclipse. That's an occulting disk sitting on the spacecraft in orbit, and it's blocking out the sun. The little white circle in the occulting disk is actually the sun behind the occulting. The black arm you see extending out of the lower left is the arm holding the occulting disk. We need this. It's very important because it allows us to see not what's happening on the surface of the sun, but what's happening in the corona. And this is a particularly important instrument. If the coronal mass ejection occurs, we want to know, is it coming towards Earth? Well, we want to know, first of all, did it happen? If it did happen, is it coming towards Earth? How fast is it coming? This is the instrument that provides that very valuable information. But when these big particle events occur, the bombardment of the energetic particles on the imager causes a remarkable effect. And actually, kind of watch the blizzard. That's the energetic particles pinging the lens on the camera in space. And it goes on sometimes for hours upon hours. Begs a question, doesn't it? How useful is this, a very important instrument during a big radiation storm? Not very useful. We can no longer use it for hours upon end when these big radiation storms occur. The geomagnetic storm is the last piece of those three different types of emission we talked about. It is, for the most part, I'm cautious when I say this because a lot depends on which sector you're talking to, but this is the one that got the interest of the folks in the White House, in the UK Parliament. In Australia, later on this year, there'll be meetings to discuss a national strategy on space weather. I was in Korea last week. They have done a lot of work. So a lot of things happening around the world. This is one of the key pieces, though, is the geomagnetic storm. It's a coronal mass ejection we're talking about. And the image there you'll see on the left-hand side, a coronal mass ejection in a still shot. The little picture of the Earth there gives you some perspective. But essentially what's happening here is the solar flare occurs in a sunspot region. There's magnetic field extending out from the sun, very complex, twisted magnetic field lines, distorted and twisted to such a degree that sometimes the pressure gives and there's a release of energy. Picture taking a rubber band and twisting and twisting and twisting, and finally it snaps. That's what's happening here. Those magnetic field lines are sitting there on the surface of the sun, extending upward, and all of a sudden the complexity is so great, the eruption occurs, and the CME gets shot, the coronal mass ejection gets shot out into space. I'm going to put this into motion, the one on the right-hand side, just to give you an example of what one looks like from the NASA LASCO instrument. And you'll just see the bright material shooting off from the sun, but I want you to pay particular attention to the structure, the bright lines. That's the magnetic field. That's that plasma just clinging to the magnetic field. That's the magnet that just got shot into space. Watch it happen here. If that's coming towards Earth, we're going to get real busy real quick. I'm going to put this animation our colleagues at NASA put together for us to just kind of summarizes this coronal mass ejection story. It's just an animation, but you look at the upper left, right-hand side, that bright area, that's the active region of the sun where the sunspots are, and boom, there's that coronal mass ejection making its 93 million mile transit to Earth. Bang, hits the Earth's magnetic field, strips back magnetic field lines. We get what's called a reconnect on the backside of the sun. Energy comes flowing in, concentrated in the polar regions. And what, of course, is the beautiful, visible manifestation of this otherwise horrible process? Aurora Borealis. I got a call from someone in Australia last, 2 years ago, and they asked me what the chances were for them to see the Northern Lights. It was a particularly strong storm, but it wasn't that strong. So the Southern Lights, of course, is the Aurora Australis. The geomagnetic storm impacts are significant too. Impact a lot of different technologies. GPS can be interfered with. This is what causes big problems to the accuracy of the GPS systems. But the one I just want to focus on more than anything, and it's such a critical piece, just in the interest of time, is the electric power grid. That CME impacts Earth's magnetic field. The fluctuations generate current above, which manifests themselves down here on Earth, on the surface of the Earth, in measured electric field. We measure it in volts per kilometer. That in turn induces the current that will flow into anything that looks like a big long antenna. What's our big long antennas? Electric power grid, the pipelines, and the railways. Essentially, those three are the biggies. Once that induced current in the electric power grid, it can lead to transformer saturation, voltage drops, and in the worst case scenario, grid collapse. Now the story is frightening to some degree when you understand the vulnerability, but it was worse in the United States when we presented this particular point, and that was that the United States, the northeastern part of the United States, the corridor between Washington, D.C., and New York City may in fact be the most vulnerable area in the world to this phenomenon. Why is that? It's northern latitude. The geology, the ground conductivity and resistivity plays a big part into dictating, influencing the vulnerability. So that plays in the northeast United States. We have, of course, a very high interconnected extra high voltage grid running up and down into Canada throughout the northeast. And even the proximity to that great conductor, that body of great conductive material, the Atlantic Ocean, saltwater body, all contribute to making the Northeast one of the more vulnerable places in the world. That was going to get the attention of folks in Washington, obviously. A point we always make, again, it gets back to sometimes people say, how real is this threat? I like to show people this is not theory, this has happened before. It just hasn't happened at a grand scale. What we have seen is this. If you look at the Hydro-Quebec press release, that was March of 1989. A particularly strong storm, not extreme, but a strong storm impacted the grid in Montreal, bringing it down, a blackout. Right below that is the September 1990 events, which impacted a lot of our transformers in our nuclear power plants, particularly Salem and Hope Creek in New Jersey, 3 Mile Island, all felt the effects of that particular geomagnetic storm. And more recently, on the right-hand side, on October the 31st, those Halloween storms, you'll see reference to the grid outage in Malmö, Sweden. I also wanted to point out that, while not included in there in any text, the folks in South Africa took a fairly significant impact during these geomagnetic storms. And those transformers, the actual visible damage you see to the transformers here, were the Eskom network transformers in South Africa. So again, recognize global impact. Now, I just wanted to touch on extreme space weather before we finish up with just some of the response activities, because this issue of extreme space weather was a huge motivator behind development of strategy and action within the White House and other leadership around the world. And a lot of it has to do with this particular event, September the 1st and 2nd in 1859, the Carrington event. An astronomer in England, back since the beginning of the early 1600s, we've been watching the sun since the telescope, Galileo and others invented, and we've been monitoring the sun and the sunspots since then. So we actually have a great record of sunspots that date back hundreds of years. The image you see up in the upper left-hand side is Carrington, the astronomer Carrington, September the 1st, doing a sunspot drawing with his telescope in England, and something funny happened. These bright shapes, these bright kidney-shaped things appeared on the image all of a sudden, and he didn't know what caused it. What he was looking at was the first solar flare. It was also, by most accounts, the biggest solar flare that we may have observed in the last, some would suggest, 500 years. How do we know how strong that particular storm was? I was kind of kidding about it a few minutes ago about the aurora, the northern lights being visible in Australia. But in this particular situation, think about our friends in Canada, Scandinavia, and elsewhere used to seeing the northern lights. What was it like in September 1859 when the folks in Cuba, Jamaica, and Mexico looked up and saw the aurora borealis? A proxy measurement of how strong the geomagnetic storm was, the aurora was visible that far south. 1921, there was another big storm. This one, if you read that, I always love reading the old historical write-ups of these events, and from the one on the left in particular, the New York Times, if you read down, you'll see that the switching system of the New York Central Railroad below 125th Street put out of operation, followed by a fire in the control tower at 57th Street and Park Avenue due to the induced current in the railway back then. Those two events in particular, 1859 and 1921, have essentially established the benchmark for us on how big is big on space weather. We've had nothing that big since, or even close to the 1859, and of course that's our fear. Should we, what would the consequence be? The last piece I wanted to touch on the extreme space weather is a very important piece, and it is this. On July the 23rd, 2012, we had a very big space weather event. Now you might say, it couldn't have been that big, I didn't hear about it. Well, take a look at the blue image. Just take a look at the yellow image first of the sun. Now see how blank it is? There's no sunspots. There was nothing happening on the sun that day. I was in the forecast center, and those energetic particles I was talking about earlier, we see them rising on our instruments on geosynchronous orbit. Why are they rising? Nothing is happening on the sun that we could see on the front side of the sun, but we turned our attention to that blue image, and we could see that coronal mass ejection. You see the material blasting out right there? That is a powerful coronal mass ejection. Now, fortunately, NASA had a couple of spacecraft on a particular mission. It was called a stereo mission. Stereo, by its name, hints what it was: two spacecraft that were on orbit around the sun. So we were able to turn our attention to one of the stereo spacecraft to take a peek at the far side of the sun and see what was going on. And when we looked, we saw that. In that lower right-hand corner there, that bright area was a magnificent, tremendous large solar flare. It, of course, was producing, on the blue image, the coronal mass ejection. The key to the story here is it was not Earth-directed. It was going the other way. Had it occurred 7 days earlier, it was going to be coming towards us. The sun rotates 27 days for a full rotation. So it was about a week or so earlier, 10 days maybe, that sunspot cluster that produced that powerful eruption would have been facing Earth, and we would have got the full brunt of this coronal mass ejection. Some of the scientists looked at this, and that was their conclusion, that it would have likely produced a storm comparable to the largest event of the 20th century. Now, some of the scientists like to say we'd still be picking up the pieces had that hit us. Hard to say, of course, but we do know this, that when that CME hit the stereo spacecraft that gave us those pictures from the backside, from the far side of the sun, it was Carrington-like, the measurements were. It was that fast, it was that intense. So the bottom line, these coronal mass ejections happen fairly frequently. Just to be the perfect storm, of course, they have to hit us here on Earth. And from the Engineering News Record, this is quite recently, this is June 22nd, 2017, so it's just weeks old. They've been looking at one of the things, obviously, from risk management is we have to understand what is the likelihood of this event, the frequency of this event. And you'll see here that they estimate there's a 10% chance of a Carrington-level event over the next decade. That, folks, is a very, very high number. And that, too, got the attention of a lot of people. There was studies done about 5 years ago from some of the same people, and they had concluded something similar, and then we knew the numbers were high, and this was just an update, and it's still a very, very high number. So let me just finish with some of the response activities. I wanted to lay that out and just give you a sense of why space weather has garnered the attention of a lot of people, the reasons behind that. So some of the things that we're doing about it. Summer of 2014, the Obama administration, with John Brennan at the time, head of the President's Chief National or Homeland Security Advisor, decided it was time to move on this. There was a lot of unknowns, but we could not take the chance of having one of these big events occur and not be ready. There was lots of things we knew we could do, and the White House decided, let's get our heads together and let's develop a national cohesive strategy to address this particular threat. So in November 2014, they asked if I would go up and help lead this initiative, and we put together a task force. It was very interesting because who gets impacted by space weather? You've learned by now pretty much everybody. So we had to bring people in. It was a great merging of the science community. We had NASA, NOAA, National Science Foundation, the Air Force and Navy research labs, the science and technology groups within DHS and within Department of Energy, all working with the National Homeland Security folks, the Federal Emergency Management people, the DoD action field type folks, all came together in the development of this strategy and action plan. 1 year later, approximately, the strategy and action plan was released at the White House. The strategy was simply a document that provided, it was 12, 13 pages, essentially the overarching umbrella document. The action plan contained 99 different actions which defined which agencies would develop and produce which products, services, mitigating actions, and what timeline. And that now is being implemented across the United States. The 6 strategic goals contained within that strategy, establish benchmarks for space weather events, is critical. And we're just now finishing up that first piece, those benchmarks. That is, define how big is big. If I'm going to tell you, and you'll appreciate this from the engineer perspective, if I'm going to tell you you have to protect against this issue of space weather, let's say geomagnetic storms, you need to know how big. How big is big? What is the 100-year storm? What is 1,000? What is the maximum of maximum? These are the kind of things people wanted to know. This was the whole initiative with the benchmark. Let's find out how big is big. If I was to tell you folks here in this audience that it's likely Miami will get hit by a hurricane with 2,000 mile per hour winds this fall, you'll laugh me out of here because we know the boundaries, the physical boundaries. We know how strong is strong in regular meteorology. Space weather, we haven't defined that yet. Number 2 and 3 was all about response, preparedness, planning, emergency response community. 4, assessing, modeling, and predicting impacts on critical infrastructure. A key activity there I'll just mention here in a minute. 5 was for the science community. Everything we needed to do in our research, because there are so many gaps, so many things we don't understand about space weather that we have to do in the research community to improve our prediction capability. And finally, as you know, this is a global threat, requires global response. We must work together globally to address the threat. Some of the key activities. This was, again, see how recently, last month, June 2017, in recognition that we could have a long-term power outage. There are a few things that can do that. Cyber is one. Space weather is another. EMP attack another. This annex was developed and just produced to provide the federal government with the federal government agencies with some understanding of what needs to be done in the event of an extended power outage due to these various scenarios. Action 4.1.1, I just wanted to mention because it's critical, and it is this. It'll have implications across the globe, and that is working with all sectors, we are going to develop some kind of vulnerability assessment. We've got to understand just how vulnerable all these different types of technologies are. We have some understanding, of course, but we have a long, long way to go. This was a tremendous success. I just wanted to share with you. The GPS satellites have on board particle sensors. It wasn't for space weather. It's for nuclear detection, long time classified material, but it's not anymore. So we worked to release this, and just in January of this year, we've got 23 satellites, more than 141 satellite years of data that we've made available now to the research community to better assess and understand what the radiation environment is indeed in geosynchronous orbit. On the international side of the house, I just wanted to mention some of the huge amount of things that are happening. Just in 5 October in 2015, the folks here in Australia, led by the Bureau of Meteorology, conducted an exercise. I mentioned earlier there'll be an event in Sydney in November on space weather, and we will be discussing with our colleagues in Australia about the potential development of a national strategy on space weather in Australia. The US has done it, the United Kingdom have done it, Norway is doing it, Australia may be as well. The UK folks at the Royal Academy of Engineering produced a very interesting and important report on extreme space weather and its impact on engineered systems. As we develop these benchmarks, we're going to do it with our colleagues around the world, Australia, UK, elsewhere. Anyone interested in participating, we're going to reach out to all. NATO, very interested in space weather. We've been in Brussels briefing NATO headquarters on space weather on various occasions. And within the United Nations, many activities underway in various groups. In particular, I wanted to mention the one in the middle, the International Civil Aviation Organization. ICAO is in the process of defining standards. They are meeting today in Montreal on the development of a network of centers around the world officially designated to provide space weather services to aviation around the world. On the bottom, the Committee on the Peaceful Uses of Outer Space, 50 different nations meet in Boston. I go from here back to Washington and Boston next 2 weeks on the Monday the 31st of July to meet on space weather with this particular UN body. Bottom line is lots of things. This is not a US-centric initiative. It's very much a big thing around the globe. Wanted to mention this too. All I talked about within the United States was driven by the White House. The other part of government, the three arms, judicial, the legislative, Congress, the Senate introduced Senate Bill 141, Space Research and Forecasting Act in January, and it was passed in May of 2017, so just a couple of months ago, introduced down the House of Representatives, and it's got bipartisan support, so we will have legislation very likely coming from the US Congress to address this issue. So not just the White House, the executive branch, but the Congress as well. Now, I just want to finish on a lighter note, because people often ask this question, and I like to illustrate it best with this slide. It was when a couple of FEMA guys were visiting us, Federal Emergency Management Agency people were visiting the Space Weather Center, and after hearing this discussion of doom and gloom from me, they concluded all communications will be impacted on one of these extreme events, and we'll be left with racing pigeons for communications. And I had to say, no, they get impacted as well. And they do. So a pigeon, anyone here involved in pigeon racing? I see in arms. So a few people. It's a global sport. It's a global activity. And anytime there's a big pigeon race, the pigeon racers will always check the geomagnetic storm conditions, because they will not start a pigeon race if the magnetic field is disturbed. The pigeons are released, you'll see them flying around, and they're getting their bearing. Once they have their bearing, it's that magnetite, they have a magnet essentially that can sense the Earth's magnetic field, and they can make their way back home, and first one home wins the prize. But even in a moderate level geomagnetic storm, it can throw them off, and they can get lost. And I learned the hard way that some of these pigeon racers paid tens of thousands for their particular good breeding racing birds, and when they get lost, and it's because I produced a bad forecast, I assure you, I hear all about it. Was one last interesting story on the pigeons. I got contacted a couple of years ago from someone, I can't remember the name of the company, something like Serenity Doves. And I asked what they want, why was she interested in getting the space weather products? And she says, well, we're one of the companies that release the doves at weddings and funerals. And it's my understanding, she said, that during a geomagnetic storm, the doves might get lost and won't come home. And I says, you've done your homework. Very good. She says, good, well, sign me up. And I said, I will. I said, just let me make sure I understand this. So if you're standing outside the chapel with the pigeons, and the bride and groom walk out, and your phone rings, and it's Bill Murtagh with a geomagnetic storm warning, you're not going to let those doves go. And she said, that's correct. And I said, good, because I want to be there when you tell the bride that she did not get her pigeon release or her dove release because of a geomagnetic storm. Anyway, my concluding remarks. I hope now you got a sense for space weather is a concern, how significant. We're really trying to get a good measure on that. We have a ways to go. We have to understand the space environment in the context of its impact on system operations, and of course taking into consideration the interconnectivity, interdependencies of the critical technology. One thing goes out, it affects a whole bunch of things. And finally, nations obviously recognizing the global threat, we must work together to enhance the resilience across all nations to this threat as we learn more and more about it. Thank you so much for your time.